Okay, so among the constraints we discussed specifically the thermal constraints, uh, the spinning reserve constraints associated with the spinning reserve, then the offline reserve, then the other thermal constraints we talked about are the minimum uptime, the minimum downtime, and the crew constraints. And then we also talked about the costs associated with the starting of the units. Okay, the hot start cost and the cold start cost. We try to find out the mathematical expression for the costs, both the hot start cost and the cold start costs. Okay, so then we talked about some other constraints like the some of the units should be kept as must run, or if not for the full duration, but at least for some duration of the operation of the power units. Okay. Then there could be fuel constraints and hydro constraints. If hydro constraints are specifically related with the cases where you also have, besides the thermal units, you also have some hydro units to be operated to fulfill the demand. And then we reached this slide talking about the different methods for solution. And there are some early methods for solving the unit commitment problem, like the priority list schemes. Then the dynamic programming method was also employed for the solution. The Lagrangian relaxation is another method, and you can say the one of the most recent one among these four is the mixed integer linear programming method. But besides this, there is also another, or there could be other methods. Okay, specifically there could be other methods like the nature-based optimization methods for solving this sort of unit commitment problems. But in this course, we'll be talking about the priority list schemes and the dynamic programming schemes in detail. So let's take one example for the priority list scheme case. Let's say we have the units. Actually, these are the same units that we took as an example earlier in this slide, unit commitment slide. Okay, so we have again 3 units with different maximum ability, maximum output, and minimum outputs. Each unit has its corresponding heat rate expression as a function of the own unit. Okay, so the first one is the first heat rate is a function of the first unit generation. Second one is a function of second unit generation, and so on. The fuel cost is given in dollars per millions of BTU, and demand, although here it is kept as 550, but we will also show what will happen if the demand is varying. Okay, so the question is asked about you construct a priority list for shutting down, that is decommitment. Okay, so the example is shown here for decommitting the units following the priority list scheme. But of course, the same problem or same sort of problems can be also solved for starting up the systems. Okay. Instead of shutting down, you can also use the priority list based example for starting up the units. So let's try to solve the example. So first you calculate the full load average production cost. Why are you calculating this? Because actually we have to set some rule for prioritizing the units. Okay, which units will get priority number 1, first priority, then which unit will come in the chronological order, and then which unit will come. So you have to set some rules. So in this example, they are setting the priority among the units based on this full load average production cost. So how are we going to calculate this full load average production cost? This is the formula, simple formula. So first you calculate the output. Okay, so what is the output? You have the heat rate, millions of BTU per hour. This should be calculated at full load, because you remember we are calculating full load production cost. Okay, full load cost, you can say full load cost. So what is the full load cost? How much your unit will cost you? What will be your expenditure if you run your unit, let's say unit number 1 at full load? So what is your full load? Full load here means the maximum capacity, 600 megawatts. So you calculate the heat rate. Okay, you calculate the heat rate for full load. Okay, so this bar, then the subscript means that this value heat rate is calculated at the full load value. Then you multiply it by the fuel cost, given fuel cost, so it is still dollars per MBTU, and then you get some cost, fuel cost, but this fuel cost here now, so this fuel cost, if after you calculate this, thing, so you basically get full load production cost, okay. So what will be the unit? So it will be dollars per hour. So full load production cost, then you divide it by the rated capacity. That means again you are dividing it by 600. So what are you doing? Basically, if you are looking for the full load production cost for the first unit, then what you do, you simply put 510 plus 7.2 in, instead of PG1 you put 600 here, plus 100124 sorry 100142, then 600 squared. So that will give you, and multiplied by 1.1. Okay, so in this expression you put the full load value, you multiply it by 1.1. So whatever value comes, that will give you whatever you expect from this bracketed term, and then you divide it by this value 600 for unit number 1, and so on. So if I go through here process, so it is 510 plus 7.2 multiplied by, let's say for unit number 1, 600 0012142 multiplied by 600 squared. So whatever value comes, let's say that is, let's say F1, let's say for example, then you divide it by, sorry, you multiply it by 1.1. So you get the bracket here. So you multiply it by 1.1, multiplied by 1.1, divided by the full load or of unit number 1, divided by 600. Okay, this is how you do it. So if you calculate it, then you get whatever value you get, that is your full load average production cost, and similarly you can calculate for the others. So then in this, following this process which I have shown just now, you can calculate the full load production cost, average production cost for unit 1, unit 2 and unit 3. The corresponding unit will be dollars per megawatt hour. So if I'm looking for a prioritized list, which unit should be put in priority number 1? The least, the unit which is having the least production cost. For this example, it is unit number 2. So my priority order will be unit number 2 first, then unit number 1, and then unit number 3. Okay, so I have updated the list according to the strict priority ordering. Okay, and my condition for priority ordering here is this calculation or this ordering is based on the full load average production cost. So the least cost unit is put in place, first place, then the second unit, and then the third unit according to their these values. So then I update the list, okay, shuffle the places as required by the calculation, as required by the priority. Then I just include their minimum megawatt and maximum megawatt as mentioned in the example. These two columns are simply taken from the problem statement. So then the scheme, okay, so one thing, it is kept pretty simple. As an example, we are not including any startup cost or minimum uptime or minimum downtime. Simply, we are focusing on what would happen if we make a list based on make a priority list based on the unit's average full load average production cost. So then if you have a variation in the demand, then how are you going to turn them off? Remember the question said, how do you shut down the units? So first, let's say the maximum load that these 3 units can supply, how much will be the maximum? This would be 600 plus 400 plus 1200. So you see the starting is from 1200. Okay, so the maximum is the 1200, and the corresponding minimum would be what? You simply add these 3. Okay, 150 plus 100 plus 50. So you add these 3, you get the maximum possible outcome from the 3 units, and you add these 3, you get the minimum possible outcome from these 3 units. Okay, so then if the demand is reduced to 1000 and less, then you simply shut down the most costly unit. Okay, so you shut down unit number 3. So you simply go with the two highest priority units. So your second combination would be 2 plus 1. So the minimum you add simply the minimum of unit number 2 plus the minimum of unit number 1. And then for this column, you simply add these 2 plus 1. So what is 2 plus 1? Let's see. So this is 2. So this is 2. This is 1. So you have 600 plus 400, 1000. And the minimum is you just simply add the minimum and you complete the table. So then again, if the load reduces to 400 or less, you simply keep the most prioritized unit, okay, or the least cost unit. You simply run your system with that alone and you keep others shut. As I said, that the same thing can be done for starting up the units. But of course, we are keeping the example very simple. We are ignoring all the other kind of constraints related to startup costs or minimum uptime or downtime. Okay. So this example gives us a simple idea of how you turn on the units or turn off the units and how do you apply the priority list, what condition you could choose for prioritizing your units. Any question? Because we'll jump to another technique now, the dynamic programming technique. Any question associated with this example? I think it is pretty simple. Once you try to solve it by your hand, then probably it will be clear. So let's continue with our next technique, which is the dynamic programming technique. Okay, in the dynamic programming, what you do basically, you consider some states, okay? Some states, and any state in case of dynamic programming, any state will have some array of units operating, that means turned on or online, and some other units be offline. Okay? So any combination, you can say in short, any combination of units can give you a state in case of dynamic programming. Then in this case, in this example, which is going to follow very soon, we are considering that the startup cost of a unit is independent of the time it has been offline. Okay. So as you saw earlier, this specifically this line, the startup cost of a unit is independent of the time. But in general, what we did earlier, that we saw that, you see this slide, in slide number 20, we discussed about the mathematical formulation for the hot start cost and the cold start costs. So we saw that there is a function of time. Both these costs, both this startup cost when cooling, you see it is a function of time t. So what was t? The time duration. The unit was closed, was kept. Unit was cooled. And the startup cost when banking, it was also a function of time. But for this example, we are again simplifying the assumption. We are having one simplifying assumption is that the startup cost is a fixed value. Okay, it's a fixed value and it is independent of the time the unit has been kept offline. So it is a fixed amount. So the value will be given to us and we will use that value for our calculation purpose. Also it is assumed here that there is no shutdown costs. Okay. So similar to startup cost, you could also come up with unit shutdown costs, but we have not discussed it in detail in this topic. So also we are not going to take into account of this effect of shutdown cost here. That is to say, when you are turning on the units, you are assuming some cost, that is the starting up cost, but that cost is kept to some fixed value. On the other hand, when you are shutting down some units, although there could be some cost associated with that, but in this topic, in this example, we are not including it. However, in the most general case, you should keep this shutdown cost as time dependent. You should also consider the shutdown cost, etc., etc. Okay, so last one, in each interval, you you should have some minimum amount of capacity available. Okay? That means you don't allow any state or any interval, any time instant to have zero capacity. Okay, that means at least one of the units should be available for supplying the demand. Okay, so the states, let's say the states, this could be one state. Okay, so if we go through the state definition, it consists of an array of units with specified units operating and the rest offline. So one of the combination for giving us a state among the units could be all units offline, right? That is to say, let's say I have 3 units, so I could choose a state, or there is a possible state that says 0, 0, 0. That would mean that none of the units are online, but that is also not considered here. Okay, so you are not allowing that all units off. You are not allowing this state to be present in your calculation. This is what is meant here. So at least you expect at least one of the units to be present to supply the demand. Do you hear me? Hello? Hello?
Yes, sir.
Okay, because the connection was probably lost. I lost the connection and it is restored. Okay, so let's continue. So what we were saying, there would be some feasible states. The states we call feasible states. Those states which
So I can see the screen share.
okay. So probably it is lost. Okay, let me restore this. Yeah, thank you. Now can you see?
Yes, sir.
Okay, thank you. So among the states, some units or some states would be feasible. Which units would be feasible? The units which can satisfy the demand. Okay, at least the combinations which can satisfy the demand. Let's say I have 3 units. The demand is 550 megawatt. So automatically, if all the units are off, that is 0, 0, 0, none of the units is supplying anything. So automatically that state will be discarded. That is not one of the feasible units, because that combination of 0, 0, 0, that means all units are off. This combination can never satisfy the demand of 550 megawatt because none of the units are online. So the feasible states would be only those states which can satisfy the demand. Okay. These are the feasible states, and we'll consider that for each time instant, let's say for each hour, the combinations which are feasible or the states which are feasible should meet the minimum amount of capacity. We will see what these how do you actually consider, how do you actually states to be feasible and non-feasible in the when we take the example. So there is an example recursive algorithm. Here again, it is simply, you can say, looks like a mathematical jargon. But let me go through this slightly, and once we start the calculation, this will become clearer. So on the left hand side, we are looking for some cost function, okay, f cost. So we are representing the cost as by f, symbol f, and this is a cost. And this cost is actually a function of 2 things, okay. Function of 2 things. The first thing is it is a function of k, and it is also a function of I. Okay, what is k? K means the interval. Okay, the hour of a day, of a month, of anything, of a week. Okay, the unit interval. So in this example, we are considering the unit to be in hours, but this could be also in some lesser units like minutes or some higher units, but in general, hour is taken, okay, as the unit of intervals. So that means we are going to look at the demand after each hour, okay, not in between them, not after every half an hour. So for this example, we are considering that we are taking the instance or the sampled load values at each hour, hour 1, hour 2, hour 3, and so on. Then the combination means the combination among the units, okay? Units on or unit off. This information will be obtained from this value of I. So this cost we are going to actually minimize. We are looking for some minimum cost. So we are not allowing any arbitrary cost here. We are only looking for, our target is to minimize the cost over our path. So L is nothing but the progression of the algorithm, okay? What in detail we will show what is L basically. In the example, we will show what is L, how we take I, how we take K, and so on. So inside this calculation of the F cost, what do you have? What are the different sorts of cost that would give us the total F cost here on the left hand side? So on the right hand side, first element that arises, that comes, is P cost. So this is basically the production cost. So P cost is nothing but the production cost. This is your P cost, okay? So production cost for state Ki. That means for kth interval or kth hour and ith combination, what is the production cost? How do you calculate it? We will show this in the example. Then we have the S cost. What is S cost? You see S, it gives you some changeover, okay? What are the changeovers? So you are in L. So you are in the interval, or you are in the state of K minus 1 L, or K minus 1 comma L, and then you are looking to jump from the state K minus 1 at L to K at I, okay, or I at K. So you are in L state, Lth combination in interval K minus 1. That means the previous instance or previous hour, you are in Lth combination. Do you face any problem here to hearing my voice?
Yes, sir.
Yes, sir.
Is it broken or what else? It is lagging or what?
Yes, sir. Broken.
Okay, then probably it is having some issue with the BDREN. Okay, because one of my colleague, he also mentioned this. He took a class yesterday and he asked me today that did I face the same problem. I said I didn't have any class in this week earlier, so today I have a class, so I told him that I will inform him. So are you facing the same issue in other classes or what? Same voice issue in other classes?
Sir,
Then we have,
today this is the first class.
no, not today. Yesterday, did you have any class?
This is the first class that you have this week.
Oh, then we have
No,
the
sir.
same. We are having the same experience. So probably, I'm not sure. Probably you will experience the same thing. Then we have to talk to them, the BDRN guys. Okay, I don't know whether there's some issue with them because my other colleague was having the same issue. Okay, so there is another chat. Okay, so there is a request. He can listen to my recording. No problem. You can listen to my recording, but I don't know how. Yeah, the recording should be, I think, good enough to clarify the issues. So in that case, we have to continue, okay? And then I will have to talk to our head or the Department of Computer Center who are in charge of this to look over this matter, okay? But until then, we better continue. Do you have any other class today after this? Do you have any other class after this today?
Sir. Yes, sir.
Sir.
Okay. So in that case, you can also sense any difficulties in other classes. If it is common, then probably it is the trouble with the BDREN side. Okay. Okay. Otherwise, I have to look into the matters. But as my colleague said, he is also facing the problem. I mean, the students for his course is also facing the problem. So I think this is a general problem, not specifically with my case or our case. Okay, so let's continue. Hopefully the recording will be, inshallah, fine enough to understand the things. Okay, so then we have the S cost. We were talking about the S cost. This is known as the state transition cost. So let's say in k minus 1, this interval, at this interval, we were at this state L, and we were looking for the cost, the transition cost. Okay, we were at this state, then at this, from this state, if we try to move forward to this state, okay, from Lth combination, if I am looking for some different combination I for next hour, so k minus 1 is the current instant or the previous instant, and the k is the current instant or the next instant, whatever. So for this changeover, what is the associated cost? That would give me the information of the S cost. So this is S cost, the state transition cost. And then the F cost Ki is my least total cost to arrive at state Ki. So what is the third element here on the right hand side? You see, this is the F cost at Ki on the left hand side, and this is the F cost K minus 1L. So simply this is the minimum cost for the previous instant for Lth combination. So this is the minimum cost for the previous instant for whatever combination we chose, okay, the minimum cost associated with that. So and this is the updated minimum cost. So this is for the previous instant and this is for the current instant. So in total, this is the short description of this recursive algorithm, which is used basically for DP or dynamic programming. So now let us go through some more things about the search path and the strategy. Okay, what is the search path? So we talk about two things here. One is N, okay, one is X, and another one is the interval. So what is N and what is X? X gives you the information about the number of states to search each period. So by period, we also mean interval. That means, let's say we are standing here, the current, okay, let's say the current instant is K, the previous instant was K minus 1, the next instant is K plus 1. So N means, X means what are the possible states, okay, what are the available states at present, or available combination, probable available combinations. All of those would be considered within X. You see the larger brackets there. That, so let's say these are 1, 2, 3, 4, 5. 5 nodes are there. So that means 5 possibilities are there. 5 possibilities of 5 combinations are there. But by dot, 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 I mean there could be others. So probably the others are not feasible. So only these 5 are feasible, okay? So at any instant, these, let's say these are feasible, these 5 are feasible at K plus 1th interval. So I take everything inside X. Now, what is N? N is the number of strategies or paths to save. So I'm not going to save all the costs associated with the search path. Okay, I'm not going to save all 5. Rather, I may choose 4, I may choose 3, I may choose maybe 1, or I may choose N equals to X. Why are we doing this? Just for avoiding computational complexity or computational burden, or you can say just to save the computational burden. So actually there is a trade-off. Okay, when I solve this, or when you go for solving it, only then it will be clear. What is the trade-off? One can say, okay, then I will only choose 1. So N could be only 1. Okay. On the other hand, what is the other extreme? Other extreme is N is equal to X. That means I keep record of all the strategies, all the possible combinations, what is going on there, or what was going on there in the previous instant. For this case, when we have N equals to X, I have to keep record of, thousands of data associated with the nodes, because I'm searching for all the possible feasible states and I'm recording them, so that if you calculate, that becomes a large, enormous value. On the other hand, if I choose very small amount of N equals to, let's say, only 1, only the least possible strategy is saved, which is our target. In that case, you might reach to such a point where this you can't proceed with the solution. Okay? you can't proceed with the solution because you didn't save actually some of the strategies which could help you to reach at the minimum cost. Okay, so there are some trade-offs. You can't take very small amount here, a small amount of nodes or strategies. You can't take too large a strategy. Okay, so there is a trade-off. Okay, so now let's go through the problem example. So we have the unit description here in this table. We have 4 units for this example for dynamic programming method. We have the maximum capacity in megawatts. We have the minimum capacity in megawatts. We have the incremental heat rate here. Okay, remember we talked about different sorts of curves. Okay, at the start of the economic load topic, we discussed different sorts of curves associated with the units. Like there could be fuel cost, there could be incremental cost. Okay, so one method for representing, there was heat rate, there was incremental heat rate. So this example gives you some values in terms of incremental heat rate, and the unit is BTU, that is the heat, British thermal unit, divided by kilowatt hours, and these are the values. The no load cost is there. What is the no load cost? Anyone? No load cost of a unit. That means the unit is online, but it is not supplying anything because the demand is less. So even then you expect some cost here under this column, no load cost. That is basically associated with some sort of fixed cost. Okay, you have to pay the maintenance cost. Okay, you have to pay the salary of the people working there, and these sort of things which are not directly associated with the production. Okay, so these are the fixed cost or no load cost. That means even if the unit is not supplying anything, it is online, it is not supplying anything, it is rotating. Okay, so if it is rotating, you know, if it is a thermal unit, your boiler unit, your turbine units all should be running, but the final outcome is 0 because it is not required at this moment. So it is simply floating, you can say. It is online, but it is not supplying anything. But even then, you need to spend money behind the fuel which is being burned for running the turbine and burning the fuel in the boiler. Okay. So that you can say the no load cost. Full load average cost, we have already mentioned how to calculate the full load average cost. So this is that value given here. And then you have the 2 more informations, critical informations, minimum uptime and minimum downtime. So these are in hours. So that means to say, let's say, for example, unit number 1, minimum uptime is 4 hours. That means once you turn on the unit, you can't immediately turn off until 4 hours until the unit has run for 4 hours consecutively. On the other hand, minimum downtime for unit number 1 is 2 hours, means once the unit is down, that means it is decommitted. You can't think about turning it on again within the next 2 hours. Okay? Only after the 2 hours has elapsed from shutdown time, you can think about turning it on again. So these 2 columns means that. Okay, so what are the initial status of the units, which one is turned on and which one is turned off, and the associated startup costs are given here. So unit 1 and unit 4, you see a minus sign. So minus means they are offline for the last 5 hours. Okay, so unit 1 is off for the last 5 hours. Unit 4 is off for the last 6 hours, whereas unit 2 and 3 has been running, have been supplying power, have been committed for the last 8 hours. So plus means they are running, minus means they are off for this much of hours. Then you have the startup costs. Okay, we mentioned about hot start cost and cold start cost. So these are the costs. So you see there's a difference between the startup cost of unit number 4 and the other 3 units. Can anyone tell what is the reason? Unit number 4, or what could be a reason? There could be many reasons, but what could be a reason? Logical reason where you can put 0 for starting the units and no startup hours is required. That means you don't need your system to be cooled down for this 4 hours or 5 hours or another 5 hours before you turn the unit on again. You don't need any cooling time. So what sort of unit this could be? Probable unit. We talked this in spinning reserve. After the spinning, this is offline reserve. You know, we also talked about offline reserve units, quick start units. So in the quick start units, maybe the capacity is less, but you can turn on it immediately. Okay, so no cooling time is required explicitly. So accordingly, you don't have to consider any cost associated with the starting of the units. So you see the 0 here, and also in the fourth, on the last column, you see the startup hours. It is cold. That means this unit becomes cold once 4 hours has elapsed. This unit becomes cold once 5 hours has elapsed, and so on. It's clear? The third one is saying 5 hours is required until the system or the machine or the unit reaches at the ambient temperature, or you can consider it to be as cooled down completely. So even that is to say, even if you consider that, let's say your unit, this unit number 1 is turned off, but 4 hours has not elapsed. That means it is still in the hot stage, right? So if 4 hours is not elapsed, then that unit is still in the hot stage, the associated, and then if you choose to turn on the unit again, so your associated cost will be 150. You get my point? Only the cold start cost will be considered only when, let's say this has been off for 5 hours. So now you are in a position to, if you need the unit number 1 to supply the demand, then the associated startup cost would be cold start cost. Why? Because this value is basically smaller than this value. Okay, you need 4 hours to cool down, but the unit has been cooled for 5 hours. So that means it is in the cool region, cool zone. So if you now try to start up the unit, the associated cost will be cold start cost. On the other hand, if this were 3, let's say 3, anything less than 4, 3 or 2 or 1, then now if you want to turn on the units, then you have to consider hot start cost. Okay. Okay, so this is the load pattern. So that is to say 8-hour problem is given here, 8-hour duration. So starting from hour number 1. So you see, as I said, we are sampling the load values at after each hour. So at hour number 1, the load value was probably 450. Then hour number 2, only it is jumped to some higher value, higher than 500, probably 520 or something like that. Then within hour 2 and 3, the load was considered to be constant. So this is hourly basis load variation. Okay, but again, this is pretty, pretty idealized case. Okay, in general, what happens? The loads remains fluctuating, right? Load keeps fluctuating. It's never a constant line like this with respect to time. But for our example, we have taken it in hourly basis, and hourly based on each hour. For each hour, the load is considered to be constant. The load is given in megawatt, so it is megawatt versus hours. Now what we do, we first, in solving the problem, we take help of the capacity ordering. What is capacity ordering? Let us see. As we have 4 units, okay, as we have 4 units, how many combinations could be there? 2 to the power 4, that is 16. But as we said at the start of unit commitment problem, that all the 0, 0, 0, 0, when all the unit is 0, we are not going to consider it to be a state. So you see at the bottom, the bottommost row, okay, from the bottom, the first row says 0, 0, 0, 1. So unit number 4 is on. Then your maximum net capacity is how much? Okay, so you're not including the 0, 0, 0, 0 state here. The remaining are simply the binary combination of all the 4 units. Okay, binary combination, you can get from 1 up to 15, and accordingly you can fill up this, and also you can fill up this, the the last column says the maximum net capacity here, the maximum net capacity. What is the maximum? So if in state 1, unit number 1 is on, so only one unit is on. So what is its maximum capacity? Let's see. So you see unit number 4, if only unit number 4 is on, your maximum capacity is 60. This is how you calculate this column. If you, in the second state, you have unit number 1 on. Okay. Okay. So actually, there is a problem. Let me clarify this a little bit more. What you can do, this is capacity ordering. Okay, this is not binary ordering. I made a mistake. This is capacity ordering. This is not binary ordering. So you see, if it is binary ordering, what do you expect? 0001. Then what? 00. What should be the next if it is binary ordering? The first one is 0001. The next one should have been 0010 and so on, right? But here you see it is differently arranged in a different manner. So this is what is mentioned by the capacity ordering. Okay. So first you can prepare a list based on your binary ordering. Okay. First you can prepare a list based on your binary ordering, and then what you do, you shuffle the combinations. You shuffle the states or shuffle the combinations in such a way that you move from the least maximum capacity to the most or the best or the highest maximum capacity. So you see, we are focusing on this column actually. We are not following any binary sequence here. Okay, it's not 1, 2, 3, 4 up to 1, 1, 1, 1. Okay, in between there is some shuffling between the states. Why? Because we are preparing this table based on the maximum capacity, maximum combined capacity of the units. So the first one is 10001. Unit number 4 has the least capacity of 60. So that's why it is kept. Then you see, if I take only unit number 1 on, only unit number 1 is taken on, so it is 80. So after 60, you get 80. Okay. This is the maximum capacity. Then 140. What is 140? Unit number 1 and 4. Then 250. Unit number 2 can alone supply 250 and so on. You get the point? How do you prepare this? How do you shuffle them? Just you keep an eye on this value. So to start with, you can prepare the binary table. Okay, if you feel it, if you face difficulty in preparing this, looking at the capacity, maximum capacity, what you can do, you can simply prepare a binary table starting from 0001, 0010, 0011, 0100, and so on. And likewise, you can complete this. And then you simply add up their maximum capacity, whatever binary combination comes there within the these 4 columns, whatever binary combination comes, you simply add their maximum capacity and fill up this. And then what you do to prepare the capacity ordering, you shuffle between the combinations, or you shuffle between the units in such a way that this gives you in a chronological manner. The capacity is obtained in a chronological order, okay, from the highest capacity to the lowest capacity. So this is what is meant by capacity ordering. So now we talk about different cases by which we are going to solve this example. So case number 1, okay, from one case to another, we are actually relaxing some of the constraints, or we are actually considering some of the constraints, you can say. So in case 1, what we do, you simply follow the strict priority order for committing or decommitting units. What is priority ordering scheme? We have already discussed in today's class. Then we ignore any minimum uptime and downtime. So you can say this is a pretty plain or pretty simple case where we are not considering any sort of uptime or downtime. So that means, that is to say, at any instant, if I feel that I need a unit, I can automatically or I can instantly get the unit turned on. On the other hand, at any instant, if I need any unit to be turned off, I can instantly turn it off. I don't have to consider uptime or downtime associated with the corresponding unit for case number 1. then I consider that, okay, the startup cost is simply the cold start cost, and I'm ignoring any hot start cost associated with the units. In case 2, you don't follow the priority list, rather you follow the complete enumeration scheme. Okay, complete enumeration scheme. What is complete enumeration scheme? We'll show it. But still, the other three remains same. Okay, we are not considering any uptime or downtime of the units. We are again considering the startup cost equals to cold start cost, and we are again neglecting the hot start cost. And in case 3, what you do, you simply again follow the complete enumeration scheme. Now you consider the uptime and downtime. You also consider the hot start cost. That means besides the cold start cost, you also consider the hot start costs. When do you consider the hot start cost? There are some lines. You can go through it, but these things will be clearer when we take the example, okay, by some numerical value. So let me read out this. The hot start up costs are to be chosen or to be selected instead of the cold start cost when the unit downtime is greater than or equal to unit minimum downtime, or less than the unit or less than unit cold startup time. Okay. So I will show this by example when we solve the problem. On the other hand, if unit downtime, that means the time duration for which the unit has been down, if this time is greater than or equal to unit cold startup time, then you go for the cold startup cost. Okay, that means sufficient time has been elapsed to make your unit cool. So once you have your unit is cooled down, then you can choose the cold startup cost. But if your unit is simply turned off, let's say in the previous hour, it has not been cooled down. So first of all, you have to check whether the minimum downtime condition is satisfied or not. Talking about this, if the minimum downtime condition is satisfied, only then you go for checking whether the unit is still in the hot state or cool state. If the unit is in the hot state, then you choose the hot startup cost. If the minimum downtime condition is satisfied, and then you check that, well, your unit has been turned down for sufficient amount of time, then you choose the cold startup cost. So maybe it is a little bit confusing here at this point because I'm not mentioning any numerical value, but once we solve the example, I think I can explain it more nicely or elaborately. So these are the characteristics for the units. So we are again considering a straight line approximation for the cost. Okay, so to start with, we have some no load cost. Okay, we have some no load cost, and then from minimum value of P, that is the production or the output, up to the maximum value of P, this is simply a linear function. The cost, the fuel cost, is simply a linear function of this. So simply you can say y equals mx plus c. This is the slope m, this is your x, so this is mx plus whatever c is here. Here's the no load cost. Okay, simply y equals mx plus c. Now, to start the calculation, after we have prepared the capacity ordering, the next step is to calculate the unit incremental cost. Remember, in our information, in the problem statement, we did not have this value. We did not have the incremental cost value. Rather, we had the incremental heat rate value. So to calculate the incremental cost in dollars per hour, which is listed here in the last column, okay, as IC. Okay, IC is incremental cost. So you take the fuel cost from the table, you take the incremental heat rate value from the table, and you see there is a mismatch between the units. Okay, what you need the unit is in dollars per hour, but you have something like British thermal unit per kilowatt hour, the incremental heat rate. You have the fuel cost in terms of dollars per MBTU. So what you have to do, you have to get rid of this. You have to get rid of this value, kilowatt. You have to get rid of the difference between BTU and MBTU, and accordingly you simply choose this. I mean, conversions. Okay, these are simply used for unit conversion, so that from these two values you can reach here. You are looking for dollars per hour. So simply you convert your kilowatt hour to your kilowatt to megawatt, because hour will be kept here. Okay, you see we have some BTU per kilowatt hour. Your expected unit is also in per hour, so you're not playing with the hour, you are simply playing with the kilowatt. So you are migrating from kilowatt to megawatt, and then simply you are using this BTU to MBTU. So accordingly you finally reach the incremental cost value. So this second column value, it is given in the example problem. The fuel cost is given, it is fixed, taken fixed. The dollar per MBTU, it is taken fixed for all the units, 2, fixed at 2. And then the incremental cost is this, calculated following this formula above. Now we come to case number 1, where we are not following enumeration scheme, rather we are following the priority ordering. So, so the capacity ordering, you remember the capacity ordering is the same table to start with. We are going with the capacity ordering. That is to say, we are starting from the least maximum capacity to the most or the highest maximum capacity. So starting from 60 with unit number 4 only as state 1, and then moving up to state 15, which is the summation of all the units available, maximum capacity of all the units. You sum them up and you reach 690. So what is the, now here we are looking for the priority scheme. What is priority scheme? We have to set some rule for prioritizing the units. So here again we are prioritizing the units according to their full load average cost. Now this value is given in the problem. Okay, this value is given. Let us go to the problem statement. So you see in this column in slide number 30, the full load average cost is listed. So if I apply priority ordering, which one should be the first? Unit number 3, okay, because it is having the lowest cost, lowest full load average cost. Then which one should come? Unit number 2, that is the second lowest. Then unit number 1, that is the third lowest, and then the highest cost is associated with unit number 4. So the priority ordering would be looking like this: 3, 2, 1, 4. Okay, 3, 2, 1, and 4 according to the value given. So this is what is done here. So they're updating the priority ordering list, or they're preparing priority ordering list with the shuffled unit numbers. So 3, 2, 1, and 4. Okay. So after you prepare the priority ordering, what you do, now you look for the allowable states or feasible states, you can say. So what was the definition of allowable state or feasible state? We said that, okay, minimum capacity, the combination of the capacity or the state should yield me at least the capacity, maximum capacity, which can handle the demand. Okay, I mean, if I choose, let's say 60 here, if I choose this state inside my allowable state, then I cannot satisfy any demand higher than 60. Okay, this is what is meant. I can only satisfy the demand up to 60 if I choose state number 1 as the allowable state. So now let us see in this case, which are, to start with, which are the allowable states. I'm not talking about feasible state, I'm talking about allowable state. What is the allowable state here? The allowable state here is your priority based on the priority ordering. Remember, in the priority ordering, what was said in the priority ordering? We said that if you remember the priority ordering shutdown, let us have a little look at that. What we did, you see, we simply chose units one after another. Okay, so let's say this was the example for shutting down the units. If I consider it in the reverse manner, how would it look like? It would look like, okay, let's say if I choose unit number 2 first based on the priority, then the next combination, the allowable combination is 2 plus 1, and the next allowable combination is 2 plus 1 plus 3. That means before I choose 2 plus 1 here, I can't go for 2 plus 3 here. Okay, I have to follow this priority. I mean, after I turn on unit number 2, the next available unit should be unit number 1. I cannot choose 2 plus 3 here. Similarly, when I shut down the units, I can't shut down unit number 2 first or unit number 1 first. I have to shut down unit number 3 first because it is a priority list. You get my point? I have to follow the priority strictly. I can't choose 2 plus 3 instead of 2 plus 1 here, although unit 3 is available, because unit 1 has higher priority than unit 3. So both in case of turning on and in case of turning off, I have to follow the ordering. With this information, let us try to apply this for this example. So you see the red colored cells. These are highlighted cells. Why these are highlighted? Because only these units are allowable. Okay, only these units are allowable because we are considering strict priority ordering. So that is to say, I have to turn on unit 3 first. Okay, I can't choose any other units before this to turn on. Why? Because unit 3 has the highest priority, okay, with the least full load average cost. So unit 1, whenever unit 1 is turned on first alone, that should be your first allowable state. So you can't choose unit 4, you can't choose unit 3, you can't choose any others because it is priority list. What is the next choice? The next choice is, what is the next unit in the priority list? 2. So that means the next option, if you want to turn on any unit after this, after unit 3, you have to turn on unit 2. So that is your second priority. So after turning on the most prioritized unit, that is unit number 3 here for this example, you have to turn on, you have to go for unit 2. Then which one? You have to go for unit 1 from the list. So this should be the one. So you can't choose 13. You see, you can't choose 13 because 13 would give me what? 13 would give me a state where unit 1 is off, but unit 4 is on, but it can't happen. We have to choose unit 1 before you choose unit 4. So it goes like this. You start with unit 3, then if you need anything, you take help from unit 2, then you need anything more, you go for unit 1, then you need anything more, you go for unit 4. Okay? When you come down in the reverse manner, so if you turn off anything, if you want to reduce anything, you reduce unit number 4, then you reduce unit number 1, then you reduce unit number 2. You get the point? Priority. You can't choose anything in between. So that's why these 4 are highlighted only. That's why these 4 are only highlighted. Are you still facing the voice issue or it was temporary?
Still facing, sir.
It's still facing. Oh,
Time to time is open.
it's a big problem. Okay. Now I go for the discussion on what is meant by K, what is meant by L, what is meant by I, and how do you calculate the DP formula, okay, dynamic programming formula. It will take a little time from us, so probably I can only start today, can't finish today, but inshallah in the next class we'll try to finish this slide of unit commitment. Okay, so let's start. We have another 10 minutes. Let's start. So we are at our number 1. So K is the current instant. Okay. So what would be K minus 1? K minus 1 is simply 0, but that is out of consideration. We don't have any data associated with the 0th hour. If you look at the load profile, go to the load profile, your system only starts from hour 1. So any information associated with the previous hour here, before I start the dynamic programming solution, I don't have any information. Okay. So K minus 1th hour for our number 1 is unknown or unavailable. Information is, you can say, missing. Okay. So what is the initial condition? Initial condition should be mentioned in the example problem. Okay, let us see whether it is mentioned or not. Okay. So how do you get the information about the initial status to start with. What is your L? You look at this, go to slide number 31, and you see that, okay, my unit number 3, you see, it is plus. So that means it is now online, and also unit 3, it is online. So my combination would be what? 0, 1, 1, 0, right? 0, 1, 1, 0. If I start from 1, 0, 1, 1, 0. So this is my state to start with. This is the initial status. It is given. It is given in this form. So all the minus signs would be considered as 0. The unit is in 0 status, and all the plus signs, unit is in on status. So that 0, 1, 1, 0, that is your state number 12 here. Okay, you see 0, 1, 1, 0. Unit 2 and unit 3 are turned on. So your initial status is state number 12. And that is, to start with, that is your L value. So now probably you are getting some idea about how to choose, or what is basically L, what is K, and so on. Okay, so what is the load? The load initially from the tape, from the curve in slide 32, probably the numerical data will be given, or if some intermediate value is given like this, then explicitly the value will be mentioned. Okay, so here it is 450 from the curve or from the data table, anything can be given, but that value should be given. This value should be given in some way. So with this demand, what are the feasible states? Okay, remember your load is 450. So now you differentiate between feasible state and allowable state. Your allowable states were all 4, okay? Because you are following the strict priority ordering, you only had 4 allowable states to start with. But now you are discarding some of them. Your demand is 450, okay? So this state number 5, can't satisfy 450 megawatt demand. So this will not be a part of your feasible states. Your feasible state would be 12, 13, and 12, 14, and 15. 5 will not be taken into account because its maximum capacity is less than your current demand of 450 megawatt. So although 5 is a part of, okay, 5 is an element in the set of allowable states, it is not an element of the set of feasible state because it doesn't have the capacity. This is the difference between allowable state and feasible state, in short. So we list these 12, 14, and 15, these 3. Why these are feasible? Because due to capacity, because state 5 can't satisfy your demand. Okay. Can't satisfy your demand. Then what was our initial state? Initial state was 12. So we list it here. Okay. And what are the feasible states? They take the value from X. Okay. So this is one of my, you see I. So this is one of the probable I. This is the next probable I. This is the another probable I. So all these 3 feasible states I list here, 12, 14, and 15. I take my current status or current state here in L, 12, 12, and 12. All have started putting the attendance. Okay, no problem. Okay, so then what is my demand? My demand is 450. I will only probably be able to complete up to this because we don't have enough time, because this needs some explanation, and then inshallah from next class I will go on with the remaining portion of the lecture. So if I am from 12 and I choose my next state, next instant to be 12 also, then the unit combination would be what? Still it would be 0, 1, 1, 0. This 0, 1, 1, 0, or this combination basically depends on the value of I. Okay, value of I. So this 0, 1, 1, 0, this comes from I. What is your demand? Your demand is 450. So you only have unit 2 and 3 to play with. So which one is the most prioritized unit, unit 3. What is its capacity? Its capacity, maximum capacity is 300. Yeah. So unit 3 has a maximum capacity of 300. Unit 2 has maximum capacity of 250. So how do you choose? In this case, you simply apply the formula that I am going to mention. You take whatever value is possible from the first priority unit. So in this case, because the maximum demand is higher than the maximum capacity of unit 3, so you simply take 300. Okay, first. The remaining you can take from the next, because now you have unit 2 and 3 turned on. So you simply choose 300 from unit 3 and the remaining from unit 2. So 300 plus 150. Probably I need to stop because everyone is focusing on their attendance and this causes disturbance. Okay, so probably I will stop because don't have enough time to proceed. But this is how you choose this one. Okay, 300 plus 150, and then you calculate the cost. How do you calculate it? I will show it inshallah in the next class. For today, I will like to stop here. And about the audio issue, probably we have to talk with our head and also the computer center so that they can communicate with the BDRN related to this issue. Okay, so please put your attendance before you leave, and once you give your attendance, you please leave the class so that I can switch off the meeting or end the meeting on time. Okay, so thank you. Let me stop the share.